Can you hear me? Mic is off. So, mic. So mic is off, Angelo.
Okay, I was in mute.
Yeah. Okay, so how are you doing?
How are you? How are you?
Yeah.
I was connected in this other gather town thing, so I wasn't sure who was speaking where. Now I can see you. So we are in Zoom. We are in the right place.
Yeah. So I'm not from that's gather town. I'm just using the Zoom. So
yes, that's what I understood. Yes. I was going there just in case, but I will actually close the other one. Yes.
Yeah.
So you speak for how long? For 45, 50 minutes plus questions?
Yeah. Okay. So, okay. So I plan a little bit longer, 50 minutes, because looks like 60 minutes talk. Yeah, it's but I try to.
So let me look at the calendar exactly.
It's kind of 1 hour, so that I thought that 50 minutes might be okay.
So the calendar says, so we have 1 hour, including questions.
Yeah. So try to finish 50 minutes. Is that fine?
Yeah.
Okay.
Yeah, 50 minutes I think is good. So if at 45, I will say to you maybe.
Yeah, sign.
Yeah. Now, unfortunately, the connection, in my parents' summer house, so the connection has been okay, but this morning doesn't want. Can you hear me okay?
Yeah, I can hear you. Yeah.
Okay.
No problem.
So are you in Okinawa?
Yeah, Okinawa. Yes. Yeah. It's very good.
No traveling.
No traveling at all. So how about you? So you where?
No traveling.
In the UK? Yeah.
No, I came to my parents' house in Sicily, in Italy.
Sicily. You came to
Sicily. As a personal.
Yeah, for summer
personal
vacation.
Traveling.
Yeah,
we are not allowed.
Vacation.
We are not allowed, of course. Yes, only vacation. We start traveling within the UK again for work, but not international for the moment.
Okay.
So, do you want to try to share the screen to see if you already have the?
Yeah. I do that. Yeah. Okay. So it's screen one.
Hi, Alessandra. Okay, June. We can see your browser. Yeah. Very good.
Yeah. Very good.
Very good. So it does work.
Yeah. Okay.
I think Alessandra is with us. Alessandra.
Hello. Yes. Hi.
Okay, there you are. Hi. So we are in the right place.
You are in the right place, of course. I'm seeing people that are progressively reaching and connecting also to GatherTown and then moving to Zoom. So maybe be patient so that progressively all the population moves to the right place. And also, if you need maybe to start 5 minutes late, don't be worried.
Okay. So June, how is the situation in Okinawa? Is it better than
what's the question?
Tokyo area?
No, I couldn't hear you.
COVID, the number of COVID.
The number of COVID.
So
number of COVID. Yeah. It's actually the density is the worst in Japan. Actually, density. So, that is because Okinawa people in a large family, so very easily to spread within the family. So that's a problem. And also, Okinawa people is a little bit, booze, they do a lot of drinking party in a hidden place. So it's not so strict like a Tokyo people.
I see.
So,
they interpret they are flexible with the rules.
Yeah. Do you have same thing, Sicily?
It's like Southern Italy. Yes, in Sicily, people are supposed to drink. But we have high numbers at the moment. More relaxed with the rules.
Okay. Yeah.
Hi, Yuki.
Hello. How are you?
You are in Tokyo, I guess, right?
Yes.
You are. You are respecting the rules, not like the people in Okinawa.
Yeah, should be strict.
I don't move
No, it's
anywhere.
A joke.
I don't move anywhere for these 2 years.
Okay.
1.5 years.
Yeah, not traveling. It's hard.
Yeah.
So we are early, so we are waiting for. So
Cindy,
any news?
It looks
say
like
it again,
you,
Yuki.
It looks like now you are on a vacation.
Yes, I'm in my parents' house in seaside. So I'm in a swinging chair. I know that's okay. For 4 more days, and then I go back to Manchester.
So how's Manchester? It's very
good.
exciting.
It was it's bigger university.
Bigger university.
We are hiring new people. It was a good move. It was good to change after 21 years. And I like the city. I like living in the city now. So I'm very happy with the move. Was the right thing to do.
Yeah, good. Yeah, great.
You went through the experience of moving.
Yeah, I do so many times. It's not.
You moved more, but yeah, you move often. It was my first and only one as a proper move.
Yeah, but I try to stay here as long as possible. I mean, until retire. So
it's a beautiful place and very good institution.
Yeah, it's kind of relaxed. So it's good.
So we will start few minutes past.
Okay. Yeah.
We will start a few minutes past 5. I will introduce you, but we are not there yet.
It's
now.
Yeah. Just a simple introduction is okay. So it's I have a
time, but we need to wait.
Yeah.
Thank you. Thank you.
So Nagai-san.
So now is the time, but
so
we will wait. Let's
Hey,
people are starting to arrive now.
So I just gave an announcement on GatherTown for people to join the Zoom room. They are progressively approaching. And I believe that if you can wait until other 5 minutes, it would be ideal because this kind of direction sometimes require a little time. So, but I will re-announce on GatherTown multiple times this, and we also sent a warning about this organization. So please just wait additional 5 minutes, and we will be able.
We will start at 5 past.
Okay.
Yes,
we will start at 5 past. Ding.
Hello, Angela.
Do you have any announcement to give? To give at the beginning of the day?
Yes, we have. In website, we have the announcement.
Okay. Do you want to give them before we start with the keynote talk?
Already.
If you want to give the announcement, maybe now, while we wait. So for people arriving now in Zoom, we will start at 5 past to allow more participants to walk into GatherTown and reach the Zoom room. Okay, just to reassure you where we are here, we are ready, but we will start at 5 past in 2 minutes. Okay, almost ready to start. Okay, I will give a brief introduction to Jun, also because my internet connection is not very stable. So just to say that it's an honor and a pleasure. We have been collaborating. We are good friends for over 10 years now. So it's a pleasure to introduce him as a friend. In addition, as a leading cognitive roboticist and one of the pioneers in neurorobotics and cognitive robotics. We know he has worked in the top institutions. We can studied in Waseda, then KAIS, and now at Okinawa Institute of Technology. And of course, we will all know Jun for his latest book, Exploring Robotics Mind. So Jun, it's your time now.
Yeah, Andrew, thank you very much. It's special. I'm happy that I was introduced by you because of like a 15 years research friends we have. Okay, so today I talk about this exploring robotic minds using the concept of predictive coding and active inference. Okay, so then my talk today is, so first I'm going to give you an overview of predictive coding, active inference under the free energy principle. Then we go to the introduction of a variational recurrent neural network model called PVRN. And then I show some robotics experiments, recent one, so using PVRN families and the social interaction and maybe goal direct planning based on active inference and also reinforcement learning and active inference. The final, I provide some kind of discussion and future perspective. So yeah, the Angela kind of introduced me about my book. Yes, I wrote a book, but 5 years ago, so it's becoming a bit old. But if you got interested in my talk today, so please look at this book. Okay, so then first predictive coding, active inference. So predictive coding is for the perception. So that one is minimizing the error between the top-down sensory prediction and its bottom-up outcome by inferring the internal states. And on the other hand, active inference is for the action generation. So minimizing prediction error by changing the sensory inputs by adequately acting on the environment. But these two are not separated process, as action and perception make a closed loop through the environment. So I'm going to show you a more intuitive picture now. So, and then, but anyway, so our group developed, is some analogous to predictive coding active inference in a relatively long time without knowing this terminology. So anyways, so we have worked on so-called something like a multiple time scale hierarchical recurrent type neural network. So then that is something like, so we have a slow dynamics part and maybe fast dynamics part is a lower level anyway. So we have some network and then we have maybe like a proprioception for the movement and the vision. So, and then branching. And then we have an intention. So the network have an intention of proactively acting or predicting for coming vision proprioception. So this is top-down pathway and the prediction and the vision proprioception. And the predicting proprioception means that predicting next time you join the angle. That's put fed into PID controller and the motor torque generated, the acting on the environment. Then we're going to have a state change, and then that results in a new sensation of both joint angle and vision. Then you may have the error between this predicted one and reality. So then that error comes. So then the error is used to further regulating the motor controller. Also, this error is bottom up through the hierarchy, and then try to minimize this error by changing in an internal state. So the update so that means that actually update intention. So from the original one that goes on every time step. So that is we have like two sides. One is changing the internal state like this one by the predictive coding. So changing internal state by predictive coding. The other side is we're going to act on the environment by active inference. Then we have both sides, top-down, bottom-up interaction, and this intricate dynamics is time developed. So then we should observe what kind of dynamics comes out. However, this is it's kind of we use is a long time deterministic dynamical model. The natural question is that how to treat probabilistic phenomena, probabilistic things. So because deterministic dynamical system is not good at treating these probabilistic things. So then, and then, so also sometime I will discuss later also, but this deterministic dynamical system is so rigid because initial state determine the future completely rigidly like a steel. So, but how we can get more kind of elastic interaction between top and bottom up, that I have been long time thinking, then could not good answer. But then it's kind of free energy things come by Carl Friston. So then that is a way to think about. So that is yeah, I started to think about that 10 years ago. So then there is a story like, so I gave a talk in the Friston laboratory like 2009 or 10 or something like that. Then after that, the Carl kindly sent me like a manuscript of the his paper, preparatory manuscript, like it's called Action Understanding Active Inference. I read it, and then he kindly, you know, in referring my work, like saying that the idea in this article can be regarded as a generic Bayesian free energy perspective on the connectionist scheme introduced by Tani. So it looks like then I noticed that what I'm doing is something called active inference. But the more important thing is that this one. So, but the Freestone is kind of cellularized this in the Bayesian framework. That is I was not so familiar with, and I'm not so good at. So then in my laboratory, so I'm discussing with Namikawa-san, my colleague Namikawa-san, or Murata-kun, Yamada-san, other people. Then we come to so taking 10 years of developing different, some variational recurrent neural network. So the difficulty is that the recurrent neural network is continuous in time and space. Then, but is free energy is more the example shown by the Friston is more discrete state. So then how to do that? But anyway, so we first developed something called stochastic CTRN by the students Murata-kun. Then, but this one is kind of random latent variable. With fixed priors allocated at the initial time step. So then, and then later this extended to the random latent variables are allocated at each time step with adaptive prior. So, okay, so then now we're gonna focus in PVRN. I'm gonna try to explain this one next. So this is called predict coding inspired variational based RN. So then that is based on free energy minimization. So we have a try to minimize prediction error. That part is same as the usual one, but also we have something called posterior and prior, and this scale divergence distance has to be minimized. And we have something the weighting factor called meta prior. I'm going to describe this later. So then the idea is something like this, so we have a probabilistic latent variable that this time steps goes, and then this goes like this. And then we have something called the sequence Gaussian prior. That's time varying Gaussian distribution, starting from the initial step with unit Gaussian, but it's developed different time varying mean and sigma, that it is multi-dimension things and go. Also we have a posterior. So then posterior is something like this one. Then we're gonna sampling. So from this probability distribution sampling, and then this one is added to the deterministic latent variable. It's kind of added. And then state transition from D1D to D3. That one is mapped to the prediction of the output, for example, joint angle and vision things and the coming. And then we have observation. So then if there is an error is propagating, back propagating, the changing this posterior in the direction of minimizing this error. So, but the important thing that we have to minimize both prediction error for this part and KL divergence between the posterior and prior this part. So then we can minimize free energy of this network. So this is something, the essential idea. So, and then this one is actually very important. So it's kind of so we examine how the internal structure develop differently depending on this value of the metaprior that I'm gonna show soon about this one. So, and a simple experiment we did first is that the learning with a very simple probabilistic finite state machine. That is, the idea is something like this. So this probabilistic finite state machine is 1, 0. Then it goes to either 1 or 0 with some probability. So this is kind of a probabilistic state, right? So then this is used for the training sequence. So that is 1, 0, then question state 1, 1, 0, 0, 1, 0 question, something like that. So this is probabilistic states part, right? Then this PVR have to learn about deconstruct this one. So that is the idea. So then okay. I hear something, somebody's eating. But anyway, so then we train the network by changing the W. So so that's a high W, large W, small W, and test generation after training with different W condition. So when we set W is larger, so this is a result of test generation. So 1, 0 output 1, 0, then it goes to 1, 1, 0, 1, 1, 0, 0. So this gray part is kind of a question state, probabilistic state, right? So then it looks like this one is extracted well. And then looking at the prior, so that is important, but it's almost 0. It goes to 0. But this one is different in the case of W set very small value. So, and the prior segment goes here is almost very small, but it's going to, this question state goes up, right? And it goes down, goes up. So this is representing like this one in deterministic and it goes to probabilistic, right? But, so the thing is that this one is, this is probabilistic structure is embedded in deterministic chaos. So it's kind of positive real exponent we found. But in this case, is that the ordinary static or probabilistic process embedded in a static dynamics. So that is the difference between 2W comes to like this one. So, okay. Then another thing, another observation is that when we set the W larger and smaller, these two are kind of extreme. So, and
somehow, Jun, you got muted.
Can you hear me now?
Yeah.
Yes.
Yeah, okay. Yeah, okay. So now, so then in the large and small setting, and then highest generalization come between. So then the point is, the important point is some. Okay, so then summary is something like this. That is, so we have fluctuated temporal pattern, and when we set W large and train them, it goes to embedded in determinist scales. But if the W set smaller, it's going to be embedded in stochastic process of probabilistic modeling. So then that is something like and then if we set W larger, high precision prior count, because prior every time step is very small sigma. But in case of set W very small, low precision prior comes. So that means that is again, this is deterministic. This is probabilistic. So, and then high precision prior means that it's kind of prediction has a very strong belief. It's estimating on prediction with very small variance. But in case of this one, estimating some kind of a mean, but a large variance, that is predicting something. But however, I'm not so certain about it, uncertain about it, right? So something like this. So that big difference. So Inference is one framework, but changing the W, we can kind of smoothly change it from the deterministic way to the probabilistic way. So that is something, I think something interesting. Okay. So then I would say that there is the Murata model, SCTR also show some kind of analogous results to this one. But in his case, it's kind of changing the fixed prior sigma. If we change, then something similar comes. So, but anyway, so in order to scale this model, so we did kind of apply multiple time scale idea to the network. So multiple time scale means that the slower dynamics part is a larger time constant. Fast dynamics part, lower level with fast dynamics with small time constant. Then learning comes from top-down prediction and goes through time. So we have a prediction like this one. Then because we have observation, then error back propagating from bottom layer to higher level through back propagating times. So retrospectively goes, right? So then we are going to updating in the old posterior as well as synaptic weights. So that is learning. So after the training or learning, and then we do kind of a prediction or post-prediction or error regression of the past after learning. So that is something like so we have so this is something in the past window. Then we predict, so this one, try to reconstruct of the past observation. If you have the error is propagating, and updating the old posterior and try to minimize free energy. So that is to making this, try to make the system situated to the sequence of sensation from the past to now. After you get situated, then you can predict for the future. So we need a lot of iteration for every sensory steps. That costs a computation, but it's necessary to do that. Then after each sensory motor steps, some iteration, then goes to next sensory motor steps. So like a robot thing, 100 millisstep, that we do the 100 epoch of minimizing free energy. That's we are doing. Okay, so then now I'm going to show some robotic experiment, but this is still a simulation, but the social interaction between two robots. Okay, so the idea is something like that. We have two robots, okay? The two robots are pre-trained for the predicting sequence of primitive patterns, which follow a specific probabilistic finite state machine. So this robot, first generating a movement like this one, then next primitive, like doing like this, C or another thing, the B, this is probabilistic, okay? And this robot also is something same structure, but after A, okay, this robot is A, then this C primitive is 80%, B is 20. But this robot is after A, C is 20%, B is 80%. So therefore, it's a little bit conflictive situation. It's so Then the training is then in this experiment set, the training is repeated with different W by looking at the effect of W for the and then different and the network trained with different W sets to the two robots. Maybe sometimes this robot trained with large W, this robot trained with small W, something like that. So then after the learning training is done, two robots interact by generating own intended movement pattern while perceiving patterns generated by the other. So I'm going to show you more an intuitive picture. So like we have two robots, and then based on the training of a different progress finite state machine, so then this robot generates kind of predicting the vision as well as a joint angle of next time step that fed into control of the movement generated and through body kinematics. And this robot can see the movement visually. So this robot also predicting the joint angle and own visual observation. So then if we have that, so then and then this robot can see this robot movement, and then the expectation. If we have the error is going to be bottom up and changing posterior at each time step. Same thing goes like this robot. So updating posterior. So we're gonna do the repeating this every time step. So in the interacting two robots interacting, that is generating own action while inferring the one by the other. So that is what we do. So specific question is what sorts of interaction can emerge? So do they always imitate each other synchronously, like a mirror neuron analogy, or do they sometimes generate own intended movement by ignoring the other? So how does W affect the way of this sort of dynamic interaction? So let's look at the robot simulation experiment. Okay. Okay, so now I'm going to show you. So the first, this robot is trained with small W. This is large W. So now both are doing A. Then go to this robot generate C and both generate C 3 times and generating A again. So actually this robot is, okay, so then generate B. This robot is actually reading. So you see that this robot, this is predicting future. This is time window, now is here, but very stably predicting. So, but this robot is very weak prediction. That is a difference in a larger W, small W. So this is a case of the both robots set with very large W. So now both robots is doing A. Then this robot generated his preferred C. This robot generated his own B. So conflicting. So, but it's both robots generated very stably because W is large. So that is both robots ignoring each other in generating own preferred action. The last case is both robots set with small W. So it's now doing A, that is stable. But after that, it's something like it's kind of very unstable. So now both doing the C and back to the A. So you see the difference. Okay, so it goes this one. So then if you look at the plots, in case of W set small and large, and in this case, the first is that this is output, right? So the both robots, right? And then this is actually showing random latent variable. Green one is prior, and then this black one is posterior. You see some difference in case W is very small. But here, you don't see the gap between prior and posterior so much. So that is because W set very small, scale divergence loosely constrained. Therefore, it's kind of a gap. That is, yes, difference between. And then also, if you look at the, this is a higher level latent barrier, very slowly changing compared to the lower level latent barrier. So that is what we can see. So the point is something like this. So when the robot is trained with larger W, the prior becomes very steep, is precise and small sigma. That's why is posterior is attracted by prior. So that is ignoring sensation and generating own intended action. On the other hand, if your prior is set, if the W is set small, prior becomes low precision, large sigma. That's why posterior is attracted by the sensation. So that's why this robot becomes more depending on sensation. That means depending on the other. That's why this robot has strong intention, strong intention, has a leader, this robot becomes follower. So that is kind of dyadic interaction. Structure comes and depends on the W. So we also worked on real robot human interaction. So it's like okay, so then this is we do real-time interaction and doing. So this is a tour of robots trained with a set of the primitive movement, but he tried to degenerate round print by pseudo interaction. Now he is trying to induce by interacting. So now primitive C is generated. So then it's now he wants to, try to generate other patterns through. So it's a primitive generated. So it's like that. This is something like so the physical interaction between human and robot, and actually, so you can feel the intention of the robot. If the robot has a strong prior, and then the robot try to push human, but prior is because prior is not precise, then human can push it, something like that. So, okay, so now we come to the in the issue of goal planning by using active inference and extending PVR and things. So as Takazumi 1 year ago published a paper, but this was a simulation, but now he's doing it on a real robot, this tour of robots. So then okay, so the idea is something like this. So we have this is a past things, and we have error regression and the update posterior. Then, so this is kind of a minimized evidence-free energy for the past. So then we provide goal is given. Then we have a prediction for the future, and then making this gap between the predicted one and the goal. So the error is taken, and then error is back propagated. Again, we're going to update to posterior. So this is a planning for future for reaching to achieving the given goal. So that is minimize expected free energy. But so we do that real time, both of them. So both of them. So both have to minimize. So through the iteration, then after good fixed number of iteration, it goes time shifted like this one. So let's look at the video. Okay, so this robot now provided is that goal by the egocentric view, and then now robot is going to achieving the goal. So this is kind of future, this is the past, but you see the past one is also changing always. So now robot is different goal position and they try to achieving this. So he can do it. So recently he showed me, we haven't analyzed it yet, but it's kind of a dynamic replanning. So that is the human experiment interfere with the robot, kind of providing this kind of things. And now you see that a lot of fluctuation in past window, so as to create himself again. Like now it's becoming, now future plan again coming. So now situated. So then he can move this to, he can do successfully moving the object to the goal position like this. So this is, we are doing real time, but it's this video is still 4 times slower, but it costs really computation time. So it's now. So then now, but the previous work is that we are not using real vision. So it's kind of a, I would say that feature vision, like object position, because of real timeness. But so we worked on also looking at the vision and pixel vision by looking at the program of the self-organizing mechanisms for the visual attention and visual working memory. So then this is done by my previous student, Minju Jun, and my researcher, Jeff Quasar. So, okay, so then what Minju did, the first is like is using arm robot. So, and then initially block is located like this one, so randomly. So then we specify the goal image by visually like this one. This is given to the robot. Then robot have to generate the visual perceptive imagery to reaching this one. So the robot should be able to do the randomly located place, and object located different place and different configuration should be generated this one and also this one. So it's kind of, yeah. So, and then this is after a good amount of the training, right? I forgot exactly, but a few hundreds of a training trajectory. Then after the good training and this kind of goal-like planning becomes possible. So then, but the conventional approach is like a goal-like planning, visual attention, or visual working memory. Those things kind of provided by the modules and integrated later. But our approach is a bit different. That is, we consider large-scale network consisting of local network. The connectivity among local network are given. Then we do kind of the local global interaction by minimizing free energy in the learning or planning process. This is possible because all parts are differentiable. So then we look at examining the emergence of cognitive function, like the planning, the working memory, attention, those, how those things kind of developed in a pseudo interaction, in a global as well as a local interaction. So that is the things we're going to do. So I'm going to show you kind of a result after good training. So then this is the initial image of the initial image, and the robot have to achieve this. This is goal image given to the robot. So then, okay, so then I'm going to show you the visual plan robot generated. So this is generated plan. So he mentally image like this one. So now next is look at the attention of self-organized. It looks like attention self-organized such that it's kind of attending to your object to be manipulated. That's reasonable. But the very interesting part is the working visual working memory part of this one. Isn't it interesting? So like, you know, it's a kind of sequence of the static image, like a sub-goal things is encoded, right? So sequence of, and actually you don't see the robot is moving here. Anyway, so but it's kind of a static sequence of the green ones on the blue and the red one on the green. That kind of things is represented here. So the emergence is something like this. So it's kind of this is goals to be achieved. This is generated visual imagery things, mental plan, visual plan. This is a visual working memory. So the first, so here it is, visual image, it is occluded. We can see the green one, but the visual working memory, green is here. So like this, that is something like, it's systems understanding like for the object permanency. So that is, if you don't move the object, even though it's hidden, it's still there, like that one. So that is the first things of the emergent thing. And the other is, as I explained already, chunking by sub-goal structure. So you look at this one. So this is the first chunk part. It doesn't change, right? So then it goes to like this one. The blue is top on the red one. So, and then finally it goes. So like a abstract representation of a chunking structure appears. We didn't expect something like these things. So then the Minj showed me one day, and then we got very surprised, and we did analysis on that one. Okay, so then another interesting thing is that Jeff Quasar, and so this is an architecture like this one. This higher level association executive control we call. This is a multimodal LSTM. And the movement part is a stacked LSTM, and the vision part is stacked the convolution LSTM, but still it's operating in free energy things. So then, this is the first visual working memory, but he said that he would like to put another visual working memory at a relatively higher level, allowing some kind of communication between them. Then what he found is something like this, that the robot can generate visual motor plans even for the manipulating unseen color objects. So that unseen means that in the time of the training, we train the blue, green, purple, red. But now I will show that is even for the unseen object like orange one, the robot can generate visual imagery. So now look at this one. So first is a this green one is approached. Something strange. It doesn't go well. Sorry, it doesn't go well. I don't know why. Maybe something is not so good. Why? I don't think. Okay, so I try to explain this. Okay, so the first is that the robot goes to try to grasping the green one by attending this one. So attention comes there. Then pick up this one. Now pick up, then you see that the first visual working memory, this green one is gone. Then we see this is the second visual working memory, we see this one. So then time proceed and try, and then here is manipulating, kind of transforming the image of a manipulating object appear there. Then it's going to trace back. Then it's appeared here again. Then it is here, it is gone. So it's gone. Then next is grasping this unseen first time novel object of the green one, and try to grasp it. So when you grasp it, so then it disappeared, and it appeared in this second working memory, and rotating it, and transforming the image. So then now putting back to here, put on here, then image appear here. So this is buffer one, and this one is gone sometime after. Okay, I'm sorry, that's why I don't know why video is not going well. Anyway, so then so what we have done is something like this one. First attending to the green one, and then it's grasping, and this part is the mask copy to here, visual working memory 2, and then transforming. So that's kind of transforming. And then it's then here is kind of a visual working memory, first one. So you see that the green one is not here, but then it's mask copy that pasted here, right? So then what is the higher prefrontal LSTM doing? Something looks like providing parameter to this one, and the sort of affine transformation. So it's generated in lower LSTM. So it's providing parameters what kind of affine transformation do. So that is kind of executive control. And also it does kind of the executive control initiating the masked copy, which part is cut by sending parameter, then they do like this. So then, so this is case of the novel object, orange one. And then, so this one is the mask copied put here. Once put in this visual working memory, and then affine transformation like things done by the LSTM. So that is do like this. So then, and then, so the point is that so we have something like content agnostic information processing. That's the autonomously developed. So that's a content, that is image of the color objects, and the function for manipulating them, that is transforming like this one, are separated. So that is important. So that is something like, if you think of the usual generative model like a convolution LSTM, these kind of objects image, and it's moving, that cannot be separated. But in this case, because using working memory and putting here, then prefrontal part can manipulate them, whatever image coming here is affine transformation possible. So in that way, sort of the compositional things, the cutting, the pasting, and transforming, this kind of things is possible. So that prefrontal like executive controls is emerged. That is a higher level LSTM calls function in the lower level LSTM associated with some control parameter. So that is what we observed. So okay, so again, but so this is not the program we provide. Rather, this information processing structure has emerged under given constraints like boundary condition, connectivity, then this kind of things appears. So that's the important part. Okay, finally, I show some kind of, we started to kind of reinforcement learning with Kenji Doyer in my institute and with my students, so that PVRLN is incorporated with reinforcement learning. So then the habituated learning is performed through the exploration by using reinforced and actor critic things and with reward. During exploration, predictive world model is also developed. After that, after good learning, goal direct planning, the action execution for specified goals are performed using active inference. So we don't have time to explain, but again, so we do that after the learning through the reinforcement learning, we do like in goal direct planning. That is, we do again goal direct planning by active inference for future. The error regression for the past we do simultaneously. So this is a robot environment, and this is a robot, and this is the obstacle.
5 minutes, June.
Okay, so starting from this starting area, so then then the exploration is like after the good exploration, then this kind of habituated behavior is generated. So then habituated behavior developed through reinforcement learning. That's one is collision-free smooth maneuvering. So the other is something like frequently visits the fixed reward position like this one. So that one's developed. Then after that, goal direct planning is done. So that is shown, some goal image is given. So then in this case, the goal image is provided here. So then in that case, but if we do the habituated behavior, robots sometimes do the redundant behavior. But if we do the goal, ask the robot to do goal direct planning, and then robot can go directly like this one. So this is a visual plan of a time sequence, and this actual observation is quite similar. So if we do the different goal setting here, again, we see something similar happen. So that is our development. And then interesting thing is that a more habituated location can be achieved more easily in case of goal direct planning. So that means that if we ask the robot to go here, it's not habituated, so the robot cannot go. So that thing is that the robot needs to explore less habituated zone or action sequence also. That's something related to the epistemic gain, and that can be done by the controlling KL divergence between the posterior prior by changing W in the future planning. So, but that is now we are working on. So finally, I have a discussion. So why is a variation recurrent network so essential for cognitive models? That is why we believe in that way. That is a seamless interaction between top-down subject mind and the bottom-up sensory reality in analog metric space. That is, so we have a top-down and the interaction in the environment, and the sensation comes inferring. That is all the picture I drew like more than 20 years ago, like this one. But this is deterministic. It's not enough. It is not enough. It's good, not good enough, because two regions. Like because of initial sensitivity, if you provide initial states, future is completely determined. So, but we need more elastic things. So that is variation-based provides. So the variation-based accounts for the development of an elastic dynamic interaction between two sides. So that's the adaptive precision, both in the posterior prior, like we discussed. And then if we change this prior things, if we are higher level, have a more precise precision pushing to the bottom. But if you have the other way around, and the bottom up pull back, the bottom, so like pushing the pull, that this kind of elastic dynamics, like we call Bayesian dynamics, is this kind of intricate Bayesian dynamics emerge. So that is, I think, very important. And finally, is something like phenomenological consciousness is very important. So non-conflictive situation with F free energy minimized, more habituated, and everything goes automatic. So then therefore this is less consciousness. But in conflictive situation, F should be minimized with an effort. So then it becomes more deliberate and more conscious. So in the future studies, we don't have time so much, but we need more modality, including language, the multiple domain experience, and we need developmental process, and then we need to have a model analogous human brain, like executive control or metacognition. And then by having these things, then we can start to think about general cognitive mind or general intelligence. Recently, I read a good paper by KN5, and also creativity, like Nangai-san in the last day talked about. But I think that this is something related to the divergence between the posterior prior things. And the reconstruction of phenomenological experience of human also very important. The point is that if we do like this one, we can synthesize, we can put this in the synthetic robot, that we can get more emergence of the intricate Bayesian dynamics. Or after that, we can start to think about these things. That's all the things today. Yeah.
Okay, thank you. Thank you, Jun.
Yeah, thank you.
I can see some clapping here. So if people want to ask questions, you can write this in the chat or raise your hand. Alessandra will help me if the connection on my side is not good. Of course, you can also directly start to talk. I don't see any raised hand with the chat system. Okay.
There is
hi.
one, Mohan. Can you?
Hello.
Hello?
Yeah, hello.
Sorry, this is Mohan. Okay, does someone hear me? And am I allowed to speak now? Is that okay?
Yes.
Okay. Hi. Well, thanks for this talk. So, it was very interesting to see this emergent behavior. So, I had a related question. So when you talked about, say, chunking, as like, say, John Ladd does with his sword or other things like that, there is an intermediate abstraction in the sense that you may get visual sensors or something else, but then it's sometimes converted into some kind of logical structures that you then manipulate, and then you can sort of maybe go back, probe, and understand, like how this emergent behavior came about, and if some other subsequent behaviors come, then you can sort of see why and how this happened. So I was wondering, in your case, if you're dealing with raw image pixels, right? So, and if this emergent behavior come, is this reproducible and repeatable? I mean, like, can you say something about what processes led to these emergent behaviors? I mean, have you studied these? I'm very curious to see if you have any related information.
Okay, so in what sense repeatable? Repeatable with different modality or different robot setting? So
yeah, different settings. So if I change, say, objects in the scene, can I learn something from, say, the initial set of trials? So I can sort of say that under these circumstances, these kind of behaviors emerge. So now if I change the objects or some other properties.
So that is we have to look at. So that, but okay, so this experiment in actually in how would I say that? Yeah. First Minju did, and then later Jeff did, but the two models are actually not so same. It's some different, but still we see like this kind of chunking things appear in the first working memory, but the task is the same. So therefore, I cannot answer the question, but it's a kind of abstraction is necessary somewhere. So then, I mean, it looks like using working memory first. So, but I cannot theorize yet why this happens. So therefore I cannot answer. So, but at least it appears in a two different architecture. It comes out.
I can tell you why I brought this up, because one common criticism that happens with these networks is like, we don't know why this is happening. Or like, but there are this really interesting behaviors, especially with that manipulation stuff that you showed. So I was wondering if you plan to, or if you have already analyzed in some sense, like, if you can somehow repeat this and show that if there are different objects,
Oh yeah. That is we did repeat the object also. Yes, it's a different set of the object in the simulation. If you look at Jeff Quasar's paper in the appendix, because reviewer asked, so we did some different setting. So in it looks like appearing. So, but I cannot say that because we didn't check many other things. We just did this research in just recently, so these 2 years. So yeah, in order to say something more general, I have to do more experiments. So
okay, thank you. And I just one comment. So you don't use any prior knowledge of dynamics, right, and physics and other things to simplify your learning. You don't do that. It's just raw image to learning from patterns, correct?
Yeah, but we have to set some parameter like some multiplier and the number of the neurons, those things that we have to set.
Okay, no, because that might speed up your learning because you said there were many trials. But thank you. I will do this offline. Thanks.
Thank you. I can see hands from Martin, Verena, and Heran. If you ask short questions, maybe we have time for the three of you. Martin.
Yeah, thank you. Hi, Jun. Good to see you and hear your recent progress. I have a short question about the stacking of the objects. Because in our experience, what happens sometimes is that when you want to grab the next object and put it onto the goal object, then the gradients are counter. Like what happens is that the grabber stays between the target object and the goal object because they're different directions. So in your architecture, how is it happening that it doesn't get stuck, but actually really gets it right, that it first grabs it and then puts it on, because that's opposite directions, kind of. Do you have an intuition, right, that works?
What do you mean opposite direction? That's opposite direction.
When you have the object that you need to grasp is over here, say, right, and the goal object is over there, so the grabber needs to go first to here and then here, right?
But this is because after the training and the habituation generate. So then it's kind of the pass. It's first have to grasp it and then put on there. If you repeat many situations, many different locations, then that passage becomes very natural to the for the robot or network.
So is your network the hierarchy of the network?
Yeah, hierarchy of the network also. Yes,
this in a sense, right?
Thank you.
Design or maybe I don't know. It's design or but we prepare some layers, number of neurons. So
yeah, thank you.
Thank you, Verena.
Okay. Hi, Jun. Thanks for your wonderful talk.
Yeah.
I have a question about what you showed on the object permanency. And then you showed that you have this visual working memory, and I was just wondering because we've also done some work on that, and we always get the question like, do you think in humans it could work in a similar way, or can we learn something about how object permanency could work in humans from your model?
Yeah, but as you probably know that object permanency is kind of it appears in the developmental process, right? It's not through the learning of a particular task. So this is a big jump, of course, because we cannot do the training robot in multiple tasks yet. So only single task, but we show it. But it's kind of at least it's analogous, right? So, but developmental process is also developmental process. We have innate structure, innate things as a player, then develop. So very different from human, but still, I mean, if you robots is an agent and learns to predict many different situations, and then because the object permanency experience many times, many different situations, and then I think probably human get it. So of course, is our experience to simplify, to verify the human side things, but I think at least analogous.
Okay, thank you.
Thank you. Last question from Heran.
Okay. Hi, Jun. A very quick question. So you show that content agnostic operators are emerging. And do you expect that this would go up to symbol emergence and operators on symbols? And do you think that this will scale up? Thank you.
Okay, yeah, that's very good question. So that I don't know, but at least we want to have like that. So that is how much I can do it. I don't know, because only experiment successful is this case. How much generalized that's I don't know. But we are now working on using this architecture into the multi-domain, and the multi-domain which require this kind of content agnostic information processing, so required in many different places. And then we might be able to show more scaled process of content agnostic information processing. Finally, imagine some kind of a truly compositional symbol still embedded in the Bayesian dynamical systems. So that is we hope, but I don't know how much I can go. You know that I have worked on symbol grounding things like 25 years, and up now I achieve like this. Yeah, but it's still it's very small things compared to human. So
okay, thank you.
Thank you. Let's take some new stuff. So thank you. And Alessandra Dingsheng, do you have any announcements or we just do a 10-minute break?
I can just give a quick update about what will be happening next. So we plan to hold the next session on models of human and animal skills at 15 past this hour. So there are, yes, about a little break at the moment. But I will ask all people who can to actually join us sort of physically through the GatherTown system so that we can meet there. Or otherwise you can remain here on Zoom and just see what happens broadcasted.
Thank you.
Okay, thank you all, and see you back in GatherTown in a few minutes then. Bye-bye. Thanks again to Professor Jun Tani.
Thank you.
It was great.
Yeah,
Thank you.
Bye-bye. Yeah, bye-bye, Angelo.